Okay, so let's do some practice examples. So I'd like you to take a moment and look at the following 5 compounds, and I'd like you to assign them as a strong acid, strong base, weak acid, weak base, or neither. And during this time, please send me a message via chat with your proposed response for each question number, and I'll be checking the chat periodically. So let's spend about 3 to 4 minutes on this problem, and let's work through and let's assign each of these compounds as strong acids, strong bases, weak bases, or neither. And let's try to indicate the major chemical species in the solution. So let's work on that for a few minutes. And don't be shy to send me a message in the chat with your proposed response or any questions so I can provide feedback. Any questions so far? I'm not seeing many responses. Don't be shy to send me responses for each of these prompts. Okay, so to help provoke some additional group discussion, let's start with our first molecule here. Let's start with our first molecule. So H2CO3. Would someone like to provide a name for H2CO3? Would someone like to provide a name in the chat? H2CO3, yep, carbonic acid. So we've clearly established just from the name alone that it is in fact an acid. Now, is it on our list of strong acids? Is it a strong or a weak acid? Is carbonic acid a strong or a weak acid? Weak, yep, it's a weak acid. Ergo, would we expect mainly ions or molecules in solution? Would we expect mainly ions or molecules in solution? Molecules, exactly right. Okay, let's look at the following compound. This is, so looking at this NH2 fragment, so we have an amine fragment, and an amine fragment signifies what type of compound? Acid or a base? An amine fragment signifies what type of compound? Remember from our discussion of acids and bases, this NH2, yep, it signifies a base, and more specifically, it signifies a weak base. So amines are weak bases, and as a result, in solution, we have mainly molecules. So you need to be able to recognize key structural features of each of your molecules in order to assign them as acids and bases, and whether they're strong acids or strong bases. So looking at question 8, calcium nitrate. Does this have any acidic or basic functionalities? Does it have any of the hallmarks of an acid or a base? I see some students typing salt already. That's exactly right. It is neither an acid or base. Now, what is the major species in solution? So if we have calcium nitrate, will it break up to yield ions, or will it stick together as a molecule? If it's a soluble ionic compound, will we have mainly ions or molecules in solution? Ions, exactly right. So we have calcium 2+ and 2 nitrate ions in solution. Wonderful. Let's look at question 9 now. Does this have any functionality that reminds us of an acid or a base? Are there any functionalities that resemble an acid or a base? For question 9, do you think it's an acid, a base, or neither? Is it an acid, a base, or neither? And just keep in mind, basic functional groups are amines, or it can dissociate to yield hydroxide. So do we have any basic functional groups in this molecule? Are there anything that resemble a hydroxide source or an amine? And let's think about this really quickly. Do we see any acidic or basic functionalities? So this compound also is neither an acid or a base. And the reason for that is so first and foremost, there's no carboxylic acid or H+ source. Secondary, there's no amine or OH- source. So as a result, this compound is neither an acid nor a base, and we call this compound a molecular compound. Because it's a covalent compound, there's no ionic character in this molecule, and there's no way for it to dissociate to yield ions. Let's look at question 10 now, calcium hydroxide. So calcium hydroxide, what do we know about soluble hydroxide salts? Are they strong acids, strong bases, weak acids, or weak bases? So for question 10, calcium hydroxide, what would we call that? Yep, strong base, exactly right, strong base. If we look at our table of strong bases, calcium hydroxide is on the list. So calcium hydroxide in solution, will we see mainly ions or molecules? Will we see mainly ions or molecules? For calcium hydroxide, yep, we'll see mainly ions. So calcium hydroxide breaks down to yield calcium 2+ and OH-. This is why calcium hydroxide is a strong base. It generates OH-, hydroxide in solution. Wonderful. So let's keep going now, and let's talk a little bit about neutralization and acid-base reactions. So what is a neutralization or acid-base reaction? So it's the reaction of an acid with a base, okay? It's characterized by the transfer of H+, a proton, from an acid to the base. So an acid is an H+ donor, and the base is the H+ acceptor. So for example, in the following reaction, we have oxalic acid, which is our H+ source, transferring a proton to hydroxide. So hydroxide is our base, because it's accepting a proton, while oxalic acid is our acid because it's donating a proton. Does that make sense to everyone? Does everyone notice the clear transfer of a proton from oxalic acid to hydroxide? Okay, so just as a run through, in an acid-base reaction, the acid donates a proton. So the acid is donating a proton. And as a result, the acid will react, and when it loses a proton, you generate the conjugate base. The base accepts a proton. So hydroxide is our base, it accepts a proton, and in turn, we generate what is known as the conjugate acid. Okay, so let's do some labeling now. Let's do some labeling now of a sample chemical reaction. So looking at our left-hand side, what is our base? What is our proton acceptor? Which of these two compounds is our base? Potassium hydroxide or hydrochloric acid? Which of these two compounds is our base? Yep, exactly right. So potassium hydroxide is our base. And which compound is our acid? Which compound is our acid? Yep, hydrochloric acid is our acid. Okay, hydrochloric acid is going to donate H plus to our base. It's going to donate a proton to our base. And in turn, now let's do our mapping here. So our acid reacts to generate the conjugate base. So the conjugate base is the acid with one less proton. So which species is our conjugate base of hydrochloric acid? Sorry, one moment. Sorry about that. Losing my voice for a second there. So which species is the conjugate base of hydrochloric acid? Which species matches hydrochloric acid with one less proton? KCl, exactly right. So this is our conjugate base. Okay, and what species is the conjugate acid of potassium hydroxide? What is potassium hydroxide with one additional proton? What species matches potassium hydroxide with one additional proton? Water, exactly right. Wonderful, perfect. So we're comfortable labeling chemical reactions, identifying the acid base, conjugate base, and conjugate acid. Wonderful. So to delve more into conjugate acid-base pairs, there are a set of compounds that differ by the loss or gain of H+. So the conjugate base has one less H+ ion. The conjugate acid has one additional H+ ion. So for example, water and hydroxide only differ by H+. So an acid has one more proton than the conjugate base, and the acid's on the reactant side. The conjugate base, which is written as A-, contains exactly one less proton than the parent acid. It's typically an anionic species, typically, and it's on the product side of the chemical equation. So for example, HNO3 reacts to yield H+ and NO3-. So NO3- would be an example of a conjugate base. The base contains one less contains less protons than the acid, just by definition. It's typically an anionic species, but it can be neutral, and it's on the reactant side of the chemical equation. Now, the conjugate acid contains exactly one more proton than the base, and it's on the product side of the chemical equation. So for example, if we have ammonia reacting with, let's suppose, sulfuric acid, we in turn would make 2 molecules of ammonium. So this would be our conjugate acid. And then we'd make sulfate. We wouldn't technically call sulfate the conjugate base. Why wouldn't we technically call sulfate the conjugate base? So looking at our definitions of conjugates, the difference between a species and its conjugate acid or base is how many protons? How many protons difference is there? How many protons difference is there between something and its conjugate acid or base? Looking at our definitions, so just focusing on our definitions, how many protons difference is there between a species and its conjugate acid or base? In our definition. So not in this problem, but in our definition. So if we compare, for example, ammonia and ammonium, how many protons have we gained? What's our difference in protons? Just for one atom of ammonia, we've gained 1 proton. So there's only 1 proton difference between a species and its conjugate acid or base. This is important just to avoid accidental trick question responses. Okay, so let's keep going now. And let's look at different types of acid-base reactions. So strong acids will donate H+ to strong bases to form water and a salt. So for example, we can have, would someone like to provide me, what's an example of a strong acid? Let's have the class design and help me make these examples. What's an example of a strong acid that you want me to draw or write? What's an example of a strong acid? Let's get used to memorizing our list of strong acids. Not a strong base. Let's start with a strong acid. What's an example of a strong acid? HBr, sure. Hydrobromic acid, sure. Okay. And they react with strong bases. What's an example of a strong base? What's an example of a strong base we can use? From our list of strong bases in the notes. What's an example of a strong base that we can use? Sure, sodium hydroxide, that would work just fine. Okay, so in an acid-base reaction, the acid transfers a proton to the base, and in turn, we generate water, which is our conjugate acid. And then we generate as an additional byproduct a salt, which is the conjugate base. Well, the salt contains the conjugate base. So bromide is our genuine conjugate base. The salt contains the conjugate base. Now, one thing I want you to focus on, I always like to box the salt in acid-base reactions because it gives you an incredible clue on how to balance your reaction stoichiometry. Okay, let's keep going now. Strong acids, let's put another strong acid. What's another example of a strong acid for our types of acid-base reactions? What's another example of a strong acid? Sure, let's go with sulfuric acid, just so we can have some interesting stoichiometry at play. Would someone like to provide an example of a weak base? What's an example of a weak base that we can use? What's an example of a weak base? KOH is a little too strong. Let's try to find a weak base to talk about. And you can go from your list of weak bases or from your book. Sure. We can look at an amine. That would be fine. So we can look at, for example, methylamine. That's perfectly fine. Now, in terms of our stoichiometry, we need two equivalents of methylamine because our amine can only accept one proton. It can only accept one H+, while sulfuric acid is donating two H+. So we always need to appreciate our stoichiometry. So in our acid-base reaction, our acid will donate a proton to our base. And in turn, at the end of this process, we will generate a weak acid and a weak base. So strong acids and strong bases react to generate weak acids and weak bases. Okay. Let's talk about the last major example. So weak acids donate H+ to strong bases to give a weak base. Would someone like to provide me a formula for a weak acid? What's an example of a weak acid that we can discuss? What's an example of a weak acid? H2S, sure, hydrosulfuric acid. That's a good one. And would someone like to provide me an example of a strong base? What's an example of a strong base? Sure, lithium hydroxide. That's one that's new. That's good. So weak acids donate H+ to strong bases. So we have our acid reacting with our base. Now looking at our stoichiometry here, just paying attention, H2S can donate up to 2 H+ equivalents, while hydroxide can only accept 1 H+ equivalent. So to fix that, we need to have 2 lithium hydroxide molecules. So our acid donates a proton to the base, and in turn, we generate water, which is our conjugate acid, and we generate lithium sulfide, which is not our conjugate base, it's just a weak base. Any questions so far? So let's keep going then. For right now, we covered up to where I'd like for us to stop for today's supplemental lecture. We're at a good point where the next few topics are best handled and packaged together and I want to make sure we have enough time to close off this topic once I start it. So this will be a good stopping point for our supplemental lecture. And I'd like you, before next lecture, to review your strong acids and strong bases, weak acids and weak bases, and then we'll resume this lecture on Tuesday of next week. Additionally, I wanted to give everyone enough time to continue to work on their lab reports, and if they have any miscellaneous questions related to the course content, we can get those addressed. So thank you for bearing